here is the second part of radioactivity. It's the sort of revision lessons. And I'll call this 1, 2, and we're just basically filling in all the last few bits about looking more carefully about the uses of radiations and their dangers. Right, well, let's talk again about the alpha, beta, gamma, and how far and what sort of materials are able to stop them and why that might be. Okay, here we have our alpha, our beta, and our gamma. And just bearing in mind, well, let's just first of all talk about what they're stopped by. Okay, let's first of all have a sheet of paper. So this is a paper sheet. Then we will have a sheet of aluminium. And then we will have a lead sheet. Right, okay, first of all, alpha will get stopped by a few centimeters, a few sheets, let's call it, sheets of paper. Or even before that, it can be stopped by a few centimeters of air. So just traveling through air, alpha will be stopped. And when I mean being stopped, it means it loses all of its energy and its speed and it just ends up stopping. Okay, beta is a bit more successful, it's able to go through there, but usually what we talk about in stopping it is aluminium. A few centimeters of aluminium will stop all beta particles from going through. It gets absorbed by it. Gamma, however, can go through the paper quite happily, go through the aluminium quite happily, will get stopped by lead, a few centimeters of lead, or we might talk about this as being a few meters of concrete. So if you want to if you want to shield, it's called shielding, stop alpha, beta, gamma, then these are the types of things you'll need to build around whatever thing you want to stop the radiation going through. Now, why might that be? Why does alpha, beta, gamma occur in that order? Well, you need to think about, firstly, the charges that are on each of these. Let me just write in again our notation on each of these, and let's have a look at it. Right, now, when all of these three interact with any material, we call it ionizes the material. So when radiation interacts, it ionizes the matter. Let's call it the matter. And what I mean by ionize is, if this is your atom with a nucleus, radiation coming in, let's look at the alpha to start with, will knock off electrons. Get knocked off. And that, in effect, is ionizing. Now, as it knocks off an electron, it gives up a bit of its energy. So therefore it continues, let's imagine this thing then continues with a little less energy before it strikes another atom, knocks off another electron, and then it continues with a little less energy until it stops. Thinking about the alpha again, what the alpha has is the alpha has two positive charges. So not only does it knock off more electrons because of that electrostatic interaction, but also it's not moving very fast anyway. It's very heavy. So it's heavy, it's not moving fast, it's interacting a lot, so therefore it has very low penetration because it has a high ionization effect. Beta, on the other hand, is a fast moving electron with only one charge rather than two. So it will go flying past matter fast and it won't interact as much, so therefore it penetrates further. Gamma, on the other hand, has no charge, has no mass, moves at the speed of light because it's an electromagnetic wave, and so will therefore fly through most matter. It will very, very rarely interact with the matter, so therefore it needs a lot of distance before it will slowly lose all of its energy. So this idea of its penetration and its ionization is inversely proportional. So what we could say is, we could say this arrow up here, sort of the ionization, whereas this arrow down here represents the penetration. As one goes up, the other goes down. Now, obviously, these will then present very different dangers to us. So if I had these in the labs, and I'm sure you've seen them in the lab, alpha, if I was demonstrating it to the front, and you were sitting at the table, you've got no risk of the alpha at all, because the air between where I am and where you are prevent any alpha from reaching you. Beta is much more of a problem because it will reach you. Also, as well with the alpha, because your skin, alpha will strike your skin and your skin will absorb it and stop it anyway, so it's not going to get into your internal organs. Your organs inside are the ones which you want to protect from any damage. Whereas beta is a problem, because beta will get through this skin and do some damage to your internal organs, and gamma just sort of vaporizes everything en route. However, I mean, if you had something stuck inside you, so if you swallowed a sample of something, alpha is going to do the most damage. And though swallowing it sounds ridiculous, or unless you're a Russian spy and tried an assassination attempt, you will have an instance where you have medical traces, and this is whereby you have you have a radioactive isotope. So these are traces. Let's write this down. So if you have a tracer that you place inside your body, then what happens is the part of your body that's injured, or there's maybe a tumour growing or something going wrong, blood flows to that area. And if the blood has lots of these radioactive isotopes in it, then they will gather at that point. So let's imagine, I don't know, let's say a head. And inside your brain you've got a problem here. And as you take the what do we call it? The radioactive isotope in blood gathers at injury or growth. So it gathers there, and then it starts firing out radiation. If you had a detector, then you can detect where on earth that's come from, and you can look inside the body. So tracers, they look inside the body. Without surgery. Okay, so that's a really useful tool. So what type of a tracer would be best? Well, the best type, I mean, first of all, you don't want to have alpha, because otherwise alpha is never going to get outside the body. You don't want gamma that flies all the way through, so beta is a really good radioactive tracer. Not in all cases, so they'll give you an example and you'll have to then interpret that example appropriately. But beta is really, really good. But not just the type, you need to consider the half-life. Because what you don't want happening is you don't want this radioactive sample to stay in there for years and years and years and do damage. It naturally does do damage when it's in there. However, there's the payoff between looking inside your body without the surgery or evasive surgery. So half-lives, you need to make a consideration that you need to have it long enough to be able to ingest it, to get to the body, being transported by the blood, and then you being whisked away to potentially a room where they might be able to X-ray, etc., or detect that radiation, versus not staying in your body too long. So something with like a few hours for the half-life is probably appropriate for that. You don't want years or tens or hundreds of years half-life, otherwise it's going to cause damage to your body progressively. So you're bound to get a situation when you're going to have to describe what type of radiation, what half-life, and why that is appropriate. You also might get a situation where you have to describe why the ionization and penetration behave as they do. But you will need to make use of the word ionize. This is a key word, and you try and drop that into any of your answers and sentences. Things ionize, it's ionizing radiation. Excellent. What else do we need to talk about? We need to talk about how that might be detected. Very quickly, I'll just say this, that if you've got this radiation that's flying through, you might, and you're working at, say, a nuclear power station, you might want to work out whether you're being subjected to any of this. So what you have is you have this photographic film you wear as a badge, and radiation fogs photographic film. So once you have that photographic film analysed, you can see how much radiation you've been subjected to. And very interestingly as well, if you put part of the photographic film there, part of it behind aluminium, and part of it behind lead, then each patch will show you what type of radiation you've been subjected to. Okay, fantastic. Now, the last point you're going to have to deal with is this concept of nuclear fission. Okay, nuclear fission is what nuclear power stations use across the world. And essentially, now you've done electromagnetic induction, what you need to understand is that fission is just a way of producing the heat to make steam. And I'm sure you're familiar with what the steam does. The steam then goes through a turbine that creates electricity. Remember, when you're trying to create electricity, you just want to make this steam to go through turbines, so anything could work, biomass, etc., etc. In this case, it's nuclear fission. And the reason why nuclear fission is very good is because the energy release is huge. Brilliant. So, your usual setup is, and I'm going to draw this as very basic block diagrams. You have inside here fuel rods, and we'll have some control rods. Okay. And this is a very, very basic type of nuclear reactor. Now, let's just talk about the process of nuclear fission below. The process is that you have a fuel, and uranium-235 seems to be the fuel of choice at the moment. You can use plutonium, but uranium-235 is the fuel of choice. 235, by the way, is the unstable isotope. 238 is the stable isotope. Now, what happens is, imagine you have a sample of this. Now, what fission is talking about? Fission is not talking about a radioactive decay, but a splitting of the atom. And in that split, you get, as a product, two smaller nuclei, which are byproducts. I suppose you could call these the daughter nuclei. But they, in effect, are the waste. You're not interested in those. And, interestingly, you get 3 neutrons being produced. Neutron, 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 1, 0, mass, no charge. It's 2 or 3, depending upon how this split works. So I'm not going to write down what this split is, because they split differently depending on, randomly they split. But on the whole, their split produces 2 to 3 neutrons. Okay, now in that split that occurs, you get some energy, and it's this energy that you're trying to use and harness to make your steam. Now, the only question is, why doesn't this occur in nature itself? Well, it can, but very, very rarely, because what you need is a neutron to be fired in. This is a neutron. And it's called a thermal neutron to be fired in. And the reason why it's called thermal is it needs to be going at the right speed. And the wonder of this reaction is, look, I've got a neutron on this side that goes in, I get some energy out, but I also get 3 coming out the other side. And those 3 coming out the other side can stimulate 3 reactions themselves. And so therefore I could get one that can get to 3, and each of those 3 can spark off another 3, and you can see where I'm going here. We start our chain reaction. Right, so it's a self-sustaining reaction. This is great. You started off, it keeps going, which is amazing. But the interesting thing is that one that starts it off needs to be at the right speed. And similarly, these that are coming out need to be at the right speed. They're going too fast. So what you do is you put them through a moderator to make them slow enough to become thermal neutrons. Okay, so that's why you need a moderator. So the neutrons go through a moderator, come out at the right speed, and just though you don't need to understand why, what they do is they make little interactions until they slow up, and then they can find another uranium-235 and split it. Okay, so that's the use of the moderator. The chain reaction, of course, can get out of control. When you're making a bomb, you want to get it out of control. But in a fuel reactor, you want to try and control it. So ideally, you want to try and absorb quite a few of these neutrons. So you make this reaction controllable. And the way that you remove some is you use a control rod. And the control rods absorb the neutrons. So coming back, inside the nuclear reactor we have the fuel rod, which you can move in and out to increase or decrease the amount of fuel and neutrons. You have neutrons flying around. You have a control rod to absorb those neutrons, and inside here you have a moderator to make sure that any neutron that is moving around is thermal. So when dealing with a nuclear reactor, what you need to be able to describe fully is the fuel and the reaction, the chain nature to the reaction, the moderator, and the control rod. And I hope with that description you should be able to do so. Brilliant. I think that is pretty much all the radiation, all the radioactivity topic covered.